Hello, here we're going to look at Matrix.1. Why? In the modern age of technology, data is everywhere. Matrices help us organize and work with data in an orderly fashion. Matrices are very important for inventory and other business models. One of the problems that we'll do here soon is something called the ice cream problem, where we use matrices to have you get a hands-on experience with how you can use matrices to help determine quantities and amounts for a small ice cream business. Other things that matrices show up with: inventory, sports data. So an ESPN is able to tell you what player averaged 27.2 points on their 27th birthday on the 27th day of September. All those random stats they give you, they're recalling data from matrices and spreadsheets. Systems of equations, which we've did previously. Business models, spreadsheets. Matrices are all of those. And we saw that matrices are an array of numbers in rows and columns. Matrix addition. This is exactly what you thought it would be. You take the corresponding values and you add them up. Right, matrix addition, super easy. You add up the corresponding values. So you've got your orange with the orange. So we've got top left plus the other top left. Top right plus the other top right. Bottom left plus the other bottom left. Bottom right plus the other bottom right. For a final answer here, 2, 6, 9, and 5. So those are the two matrices added together. It's exactly what you would expect, right? So given that this matrix A is a 3 by 3, 3 rows and 3 columns, matrix B is a 2 by 2, you could then imagine why these matrices can't be added. They don't have corresponding values. We need identical shaped matrices, identical dimensions. So 2 by 2, 2 by 2, that's what it takes to add. They can't be different sizes. It wouldn't make any sense. Now, in mathematics, addition is commutative. For example, 2 plus 3 and 3 plus 2 are the same thing. Using the two matrices below, prove that addition in matrices is also commutative. I'm going to leave this to you, but what you would do is you would take matrix A and add it with matrix B. You would then, on a separate problem, try the other way around. What if I did matrix B first and then added it with matrix A? And you would recognize that you get the same answer for both. The matrix addition is commutative. And I'll let you, after these notes, or if you want to prove that for yourself, you can add those same two matrices up in the different orders, and you'll receive the same answer. Subtraction is very much like addition. We're going to subtract the two matrices below. This is very similar to where we have a negative out in front of a parentheses and we need to distribute. When I'm subtracting another matrix, I'm not just subtracting that value, I'm subtracting all of these. So this negative sign would distribute to all of those, which leaves you with two different methods on how you could take care of this. One option would be to rewrite the fact that you're going to add after you distribute the negative into all. So to where all of them have changed signs. So notice how I'm just going through and changing all of the signs. Once you do that, then you could take these two matrices and add them together. You could take this matrix added with that matrix because I already took care of the distributing the negative concept. Alright, and so another route that people will do is just repeat the operation over and over again, such as 5 minus negative 1, 7 minus 4. And do that for all of them, saying minus each time to make sure they keep track of it. Regardless, though, the answer for this one, so I'm going to do it from this approach to where I've went ahead and distributed the negative, and now I'll add them, we'll get this. Let's see, so negative 8, negative 2, and a negative 11. Now for this part here, it's asking, is subtraction commutative like addition? Prove whether it is below using the two matrices. Now do keep in mind that regular numbers with subtraction are not commutative. For example, 5 minus 3 is 2. If I reverse those orders, 3 minus 5, negative 2. So subtraction is not commutative. You could try it with this and say, what happens when I do matrix A minus matrix B? What happens when I do matrix B minus matrix A? You'll see that you get a similar result as what happened right here. You'll get the same values, but you'll realize that when I do them in the different orders, that one will be the opposite of each other in terms of its negative and positive sign. And I'll let you explore that if you'd like after the notes are up. Also in mathematics, we have identities for addition and subtraction. For example, 0 is the additive identity because 3 plus 0 is 3, or 3 minus 0 is 3. Matrices work the same way. So it's saying if you needed to add a matrix onto this, but you didn't want to change anything, you would need a matrix of the same size, all of zeros. If I add another 2 by 2 matrix onto this, but it's all zeros, it won't change. And you can discover this for yourself. All this page is looking at generic matrix properties, which is why I'm rushing through it. You could check that if you take that matrix and you add it with a matrix of all zeros, same dimensions, that you would get that as your answer, right? And you probably won't even take the time to do it because it's common sense. We're learning that matrices are following common sense math rules. All right. So what would be the identity matrix for this? A matrix of the same size, because that's the only requirement to add and subtract matrices together, is that they must be the same size. Here's where some math can come in on this concept of matrices. So this is where essentially you could think of Matrix.1 notes truly beginning. There may be unknowns in our matrix. We can follow some simple steps to get this set up. And it's going to follow common sense rules. Here I've got a 2 by 2 matrix. Here I've got a 2 by 2 matrix. We're going to be able to set up some equations to solve for this x and to solve for this y. All right, and it deals with corresponding values. If these two matrices are equal, then the top right components on both must be equal. So this equation would be 3x plus 1 is equal to 16. If you then solve that equation, you get that x is 5. To find the y's, the bottom left entry is equal to the bottom left entry. 2y minus 1 is equal to negative 5. When you solve this equation, you'd get that y is equal to a negative 2. But all this is hinging upon the concept of setting up equivalent parts of the matrix, right? If we have a matrix that's equal, two matrices that are equal, they're the same. And that is why you may have noticed that 9 and 10, that's the exact same 9 and 10 that's right there. Solving for x or y. This time, we've got one step in between. I cannot say, oh, I'm going to set 3x minus 3, it's in the bottom right, equal to that, because there's another matrix here in the way. This is just like solving equations. If I wanted to be able to do this, I first need to get myself back to a scenario similar to that last problem, where one matrix is equal to another matrix. I would do that by following the exact same steps that you would expect to happen on any equation solving concept, which is to get rid of the terms you don't need by doing the opposite. So in this case, I could subtract this matrix, right, from both sides. When we do that, it would free up our original matrix. And now we can set it equal to a matrix. And when I subtract these two together, 9 minus 3 is 6. 5 minus a negative 1 would be a double. Negative to turn positive. 4 minus 1 is 3. 2 minus 1 is 1. Now that we have two identical matrices, we can set them up and solve for our equations, our variables. So 3y is equal to 6. Y is equal to 2. 3x minus 3 is equal to 1. Add 3 to both sides. Divide by 3. And we get that x is equal to 4/3. It's as simple as that. It's just like solving regular old equations, except now we're working with matrices. Now, on this next problem, the entire value that we're missing is a matrix. Z is a matrix. I know that because in order for it to add with this matrix, it must be a 2 by 2 matrix. How we will find it is just like you might be already expecting and probably already working on. I would just need to subtract this matrix from both sides. And that would then solve us for z. So 9 minus 5 is 4. 0 minus 2 is negative 2. 6 minus 4 is 2. And 4 minus 1 is 3. You can even double check this, just like with regular equations. Make sure that if you add this matrix back with this original matrix, that it equals what we are trying to equal to. 5 and 4 is 9. Negative 2 and 2 is 0. 2 and 4 is 6. 3 and 1 is 4. Let's take a look at this one to conclude. The first table shows the teams with the 4 best records halfway through their season. The second table shows the full season records for the same 4 teams. Which team had the best record during the second half of the season? So this is an example of us using matrices with sports to answer some questions that you may be curious about when you're debating sports with your friends. I encourage you to take a moment to think about how you could use the records for the entire season in combination with the records for the first half of a season to come up with a third potential matrix that shows which teams had the best second half of the season. I'll let you think about that here for a moment. And if you are proctoring this video and you want to have a conversation about it, feel free to pause and discuss with the class. Hopefully you've come to the conclusion that if we take the records for the entire season, I need to increase my matrix size here. And we write down these values. Which represent the end of the season. And then we subtract the first half of the season we would be left over with a wins and loss matrix, right? So it'd still be the same columns of wins and losses that would represent the second half of the season. So I would encourage you to do that. Take your different results, right? It'll be color-coded just like you'd expect. And fill that out and determine which team had the best record for the second half of the season. This is an example of what matrices can have us do. Is it complicated? No. Do we spend hours and hours of our lives watching sports and talking about things like this, if that's what interests you? Yes. Matrices can help us use data, work with data like this as we wanted to look at scenarios such as who had the best record for the second half of the season, or all those different types of fun sports stats that we love.